Okay, today we're going to be talking about the projectile motion post lab. So in this lab, we study the motion of a ball being thrown across the room from one person to another. Here's a sample of what your Logger Pro video would have looked like after you did all your clicking. In this video, a ball was thrown from left to right, and you can see that there's our scale with our meter stick, and it created a parabolic shape after all the clicking was finished. So after the lab, I had you whiteboard the results of various graphs. One important one that I want to talk about is the position time graph for the x direction, or the horizontal direction. If you did this lab correctly and properly, and you were very careful with your clicking, you should have found that this graph was a linear line. And we can tell it's linear because it has a correlation of 1.0. So that's a straight line. And we can tell that in the x direction has a velocity of about 3.08 meters per second. And we can also tell that it's traveling in the positive direction, which makes sense because the ball was thrown from left to right. So as far as the horizontal direction is concerned, it was traveling in the positive direction, left to right. Most importantly, you want to take note of the fact that this is a straight line. Again, in the x direction, we have a constant velocity. Now, if we take a look at the position graph of the vertical direction, or the y versus time graph, right? Y because it's vertical, we see something completely different. We see a parabolic shape. Okay, so qualitatively, we can tell that first it travels in the positive direction. And note, in the positive direction, when we're talking about vertical, that means it's traveling up. And then it travels in the negative direction. And that means, vertically, that means it's just traveling downwards. By the shape of the graph, we can also tell that it's clearly not a straight line. And typically when we see curved position graphs, that will tell us that an object is accelerating. So what we know from this position time graph is that in the y direction, it's not linear, therefore it's accelerating vertically. Now the other graph that I'm going to take a look at is in the vertical direction, but this time it's a velocity time graph. So it's the velocity time graph for the previous graph, for the y versus time graph. And what this tells us is now we have a straight line. The thing is that it's a velocity graph. So still, the object is accelerating, and it's actually accelerating based on how I clicked, was negative 10.53 meters per second per second. Now, with these video analysis labs, it's very difficult. You have to be very careful with how you click. This number is extremely close to an acceleration that we've talked about before. In fact, if I was able to do pixel perfect clicks, I would have gotten a slope of negative 9.8 meters per second squared. So as far as the y direction, or the vertical direction, is concerned, this ball is in free fall, right? It's accelerating at a specific rate in the vertical direction. So we have an interesting situation here because half of our data in the x direction says this ball is not accelerating. And then the other half of our data, everything in the vertical direction, says that the ball is accelerating. And not only that, it's accelerating at negative 9.8 meters per second squared. So we want to get a better understanding of what this data is really telling us. And what we're going to do is take a look at the motion maps that we would see or draw if we were to look at the speed of the ball. Now, this is a motion map. If I were to only look at the velocity vectors that happen in the horizontal direction. Now, if the ball was traveling up and then it travels down, it does create that parabolic shape that we saw from our clicking. So that's not supposed to be a big surprise to us. And based on what the horizontal graph was telling us, it told us that the velocity was constant. So these red velocity vectors are all the same length. So the thing here is, as far as projectiles go, when an object is thrown across the air, traveling in 2 dimensions, what we have here is in the horizontal direction, it's doing its thing of traveling with a constant velocity, but at the same time, it's also doing a thing of free fall where you throw something in the air and it does make a parabolic shape. So let's dig a little bit further. Okay, and here I have the motion map if we were to only look at the velocity vectors that take place in the vertical direction. So here in the initial position, it starts off traveling in the positive direction, and it's the fastest there. It starts slowing down, still traveling in the positive direction, and as far as the y velocity or the vertical velocity is concerned, it stops at the top for less than a split second. So it's slowing down as it travels upwards, and it speeds up as it travels downwards, all the while also moving to the right in constant increments, or in the constant velocity. Okay, so as it turns out, both things are actually happening at the same time. If you were to somehow be able to just look at the projectile with the horizontal direction in mind, it does travel with a constant velocity from left to right. Now, if you were to also just pay attention to the vertical motion, you'll find an object that's accelerating downwards with a rate of negative 9.8 meters per second squared. So in the horizontal direction, we have the object traveling at a constant velocity, and in the vertical direction, it's accelerating downwards. And that's due to the fact that if we were to draw a force diagram for the projectile, what we would have here is just the force of gravity, and that would just be it. And I'm neglecting air resistance here. So we would have the force of gravity on the ball by the Earth. And this is why in the vertical direction, we only have acceleration in the vertical direction. And that's why in the horizontal direction, we have the ball traveling with a constant velocity, but because there is no force, there's no net force acting left and right. The only net force is acting vertically. So that's why it only accelerates vertically. So the good thing about this unit is that our equations we have already gotten at the beginning of the year when we did Unit 2, constant velocity, and Unit 3, constant acceleration. For the horizontal direction, we have our constant velocity equation. All I did was change it here. This is our usual constant velocity equation, and all I did was bring the initial position over to the other side. Right, so you want to keep in mind again that x minus x initial is just a delta x. So that's where I got this. And the horizontal equation you want to use when you're solving for how far. And that's also known as the range. So that will tell you how far it travels horizontally. Now, in the vertical direction, I could ask you various amount of questions. For the vertical direction, usually what you want to do is for the vertical, this is really associated with how high, right? How high is different than how far. How high talks about the vertical direction. So these three equations are the usual equations 1, 2, and 3 that we all know from Unit 3. Now, the only difference is I've turned all the x's into y's. So every velocity you'll see it now has a subscript y, because we need to denote that there's a different velocity in the y direction and the x direction. Those two things are completely different from one another. We'll talk more about that in class, but they are different from each other, right? We know that the velocity in the x direction never changes, and in the vertical direction it does change because it's accelerating. So in short, that's why you want to denote the difference between the two. We also have that instead of my delta x, I have just delta y, because that's kind of like the displacement in the vertical direction. So we want to note those differences as well. But otherwise, these equations work exactly the same as they did in Unit 3. So for this unit, in total, we'll have 4 equations that we want to work with, and there'll be proper times to use each one. So likewise, if you're one of my honors students, we will do some problems with initial position, whether it's in the x direction or the y direction in his initial position. So in my honors classes, I don't like to bring those together and do a triangle x or a triangle y, delta x, delta y. I like to keep them separate because it keeps our options open in terms of problem solving. So really the only differences here that you'll see is the added subscripts for the x's, added subscripts for the y velocities, and I've just turned the x's or the positions into y positions. And that's pretty much it. We'll talk more about practice problems later on in class, and I'll see you later.